A few weeks ago, we were introduced to really the first model of the inside of an atom when J.J. Thomson discovered the electron and he proposed the plum pudding model of the atom, where electrons were essentially dispersed within kind of a framework of positive matter inside of the atom. And we said, this was not a very good model. It's not how we view the atom today, but it was the first attempt to model the atom, and that's why it's important. It's how science works. We propose a system or a model, and we use evidence to refine or replace that system. And so here we are again, this time looking at the work of Niels Bohr, who's famous for his planetary model of the atom. And I have to say, right from the very get go, that his model of the atom is also not perfect. It is certainly not the model of the atom that we use today. But it was that next great step that took us to a further understanding of what the atom looks like and how electrons behave within it and interact with the nucleus that's associated with it. So, in this video, I just want to, before we jump into the details of Bohr's model, I want to spend a little bit of time just talking about some of the basic principles that Bohr would have been using as he developed his model. And the first is to look at the relationship between the electron and the nucleus. We know electrons have a negative charge. We know from Rutherford's work that the nucleus is positively charged, and we know now that that's because there are protons within the nucleus. And we know that opposite charges attract to one another. And so when that happens and an electron is close to the nucleus, um, we produce some very important concepts that pretty much run all the way through the narrative of chemistry. Number one is this: that when we have a strong attraction between particles like an electron and the nucleus, that produces stability. There's a stable connection between those two particles. And for chemists, that means that energy is low in the system. And in general, systems do revert to low energy. So, not to characterize this as good or bad, it's just what systems tend towards is a low energy relationship. So that electron being close to the nucleus is a stable low energy situation because of how close they are and how strongly attracted they are to one another. It's possible to move that electron away from the nucleus, but you have to feed it energy in order to get there. So some of the ways that you could do that, you could shine light on a substance and the electrons might move away from their own particular nucleus. Other ways you could do that, you could heat up a substance. That would move the electrons, that would give them energy to move away from the nucleus. And finally, you could also run a current or run a voltage through a substance, as we saw with neon lights, and move the electrons away from the nucleus. But when we do that, there is some instability that arises. Think about two magnets. When two magnets are really close together, they have a strong attraction for one another. But that attraction fades very quickly as the two magnets move apart. And it works the same way with charged particles. If I have two charged particles of opposite nature that are close together, they show a strong attraction. But as soon as I move them apart, that attraction dissipates or starts to disappear, and that causes instability. And when you have a system that's unstable, we consider that to be high in energy because they are far away. Okay. Now, things tend towards low energy, as we talked about moments ago. So, in almost all circumstances, that electron is going to find its way back to the nucleus. But in order to get there, this is the most important part of this video. In order to get there, the electron needs to release energy in some way. It needs to get rid of that excess energy it's taken on. And the way we're going to find that that happens in the atom is electrons tend to release light as that source of energy to help it get back to a relaxed or ground state near the nucleus. So just to summarize what we've said here so far, when an electron is close to the nucleus, that produces a strong attraction for the nucleus. The atom is more stable, and we would say that that means the atom is low in energy. And that's a good thing. When the electron is farther away from the nucleus, it has a weaker attraction, just like two magnets that are far from one another have weak attraction. The atom is less stable, and therefore it's going to be higher in energy. When we come back, we're going to take this premise that we've established here and use it to kind of follow along with how Bohr envisioned the atom in his planetary model. Until then, we'll see you next time.